Today we will see a very important algorithm in graph theory. It's called Dijkstra algorithm. It's used to find the shortest path from a source to all the other vertices in the graph. So it can be used in multiple forms. For example, you may just want to know what is the distance of each of these nodes from the source vertex. Additionally, you may like to calculate the shortest path as well, not just the distance but path as well. Then you can store one extra variable. So first we will see the algorithm and then we will run through an example, this sample graph, in order to understand the concept better. So let's see the algorithm. So here you are given a graph and a source vertex, and we have to find shortest path from source to all vertices in the graph. And you may not require paths in some problem, you may just need the distance of each node from the source. So we will try to run through examples which cover both the scenarios. So the algorithm is that given a graph, initialize all the vertices distance. So you assign a distance level to each of the node in the graph, and each vertex is assumed to be at a distance of infinity from the source in the beginning. We don't know the distance, we also don't know the path. So set everything to every distance level to infinity, and for the source set the distance to 0. Since we know this thing, we know in the beginning that source is at 0 distance from itself. Since if you are at some node, in order to reach here itself you don't need to travel anything, so the distance will be 0. So this we know, but other distances we don't know, and we are setting to infinity so that whenever we get a better solution, we keep updating it. If we don't get a better solution, we will leave it as it is. So push the source vertex in a min priority queue and pop the vertex with the minimum distance from queue. So there are multiple ways of implementing it to make it efficient. You can push all the vertices in the beginning itself to the priority queue. So all the vertices are in the priority queue. Source is at a distance of 0. Rest we have a bunch of infinity. So if this is a min priority queue, then this source node will be automatically picked first. So this source has a level of 0. We will see its neighbors. Let's say we have 3 neighbors at a distance of 5, 8 and 4. These are the 3 nodes. So wherever these nodes are, we update their values. So we see if 5 is less than existing level or not. Yes, so 5, and let's say this was this node, so we make it 4, and this one becomes 8. Now this 0 is popped. We have finalized its distance. It cannot change in future. So this is popped from the priority queue. Now these are the elements. So what will be at the root? This node. The distance 4 will be at the root since this is the minimum. So next we will pick this node, and we will see what are the neighbors of this. Let's say this node whose distance is 8 from source is also a neighbor of this 4, and let's say this distance is 3. So we see that we can reach this node in 4 units. So this is at 4 units from source, and from here to this node, if this is A, this is B, from A to B it's 3. So from source to B we can reach in using this path. Let me draw in different color. So we can take this yellow path, we can come to A, and then from A come to B. So total length will be 7, 4 plus 3. So this is better than our existing path. So we update it to 7. And this is finalized now, 4. So whenever we pick the minimum and pop it from the priority queue, that distance is final. So we are left with one less vertex in this priority queue. Now next this node will be picked. It is the minimum in this priority queue, 5. So again we will look at its neighbor and so on until this priority queue becomes empty. And the optimization is that you don't need to push everything in the heap in the beginning itself. Just put source distance equal to 0 and just put this node in the priority queue. So there is just one node, source, with a level of 0. So once we pop something out of the priority queue, we look at its neighbors, update their distance labels. So for in this case example 5, 8 and 4, and put these in the priority queue, because minimum will be only from these. So these are in the priority queue now, 4, 5 and 8. So next we will pop 4 and then look at its neighbors. So this was updated to 7, and we will also insert some more nodes which we discovered. So that way you will have less number of nodes in the priority queue. If you insert it in the beginning, it's much more simpler to insert everything in the beginning and not worry about insertion in future, just popping. But you will have more number of nodes in this case. In this case you will be working with lesser number of nodes. So I hope this is clear. Let's run through an example and it will be even more clear. It's better to understand it with the help of example. So let's say A is the source. Source is node A. So what will be its level? Its level will be 0. So A is at a distance of 0. Everything is in priority queue. So 0 will be picked, this node A, and then let's color it in red so that its distance is finalized now at 0. And then its neighbors are this B and D. So initially these are infinity. Everything else is infinity apart from the source. This is in the beginning. This distance is finalized. Its neighbors are B and D. So we see whatever node is popped from the queue. So let's say U is the extract min from priority queue. Let's say everything is in queue in the beginning. So U was this node A, since its level was 0. Then we look at all the neighbors for all V adjacent to U. What we do, we see if distance of U, that is the node that we popped, plus V is adjacent to U, so there will be some length L U to V. Let this denote the distance between U and V. So in this case, for example, this is LEC and this is LCE. Both are different. This is directed graph. So this denotes the length of the edge. So if you come to U, the distance level of U plus take this edge is less than the distance of V, the existing distance of V. So we had some distance of V, we found a better path here. So come to U and then take this edge. So you will get a better solution. Then we update V, this level, du plus LUV. So we do this for all the neighbors of U, the node that was popped. And we keep on doing this until the queue is empty. Until queue is empty. And finally, the final levels will be the shortest distances from source to all of those nodes. And here one extra thing you can do, if let's say instead of just distance you are interested in the actual path. For example, the shortest path to C can be you come to D and then you take this, or it can be ABC, so you don't know. So let's store the previous node. So here whenever you find a better path, you also store an extra value, prev V equal to U. Why? Because you come to U, this is U in the beginning, and from there you take an edge to reach a vertex V. So you came to U from V. This is the best known path till now. Whenever you find a new U such that from there you can reach to this V, you will update this also. So these two are updated together. And finally, when this queue becomes empty, you will have the distance level in dv and previous nodes in prev. So let's say you want to know the path from A to C. You will see what is the previous of C. If let's say that is B, you will come to B. And what is the previous of B? It may be A. So you can come to A. But here it looks like it will be 5 plus 3, 8. So previous of B will be D. And previous of D will be A. So C to A to C path will be A, D, B, C. That's why you need to store previous so that you can backtrack, and when you reach the source you stop. You print the path in opposite order. So let's complete this example. So everything is infinity, this is 0, this is finalized. Next we got a better distance, U plus LV. So here it's 10. 10 is less than infinity and 5 is also less than infinity, and its previous we have set to A, and its previous is also set to A. So next, these elements are in the priority queue. The nodes which are in yellow are in priority queue. The red one has been popped. So which is the minimum? 5, 10 and others infinity. So this is the minimum. So this distance is final. And you pop it from the priority queue now and look at its neighbors. So its neighbors are E. So its level is 5. 5 plus 2 is 7, which is better than infinity. So 7, and its previous is D. And next neighbor is C. So its 5 plus 9 is 14, which is better than infinity. And the other neighbor is B. So this one. So it's 5 plus 3, 8, which is better than 10. So we update it. So it's 8 now. And its previous changes to D. And there are no more neighbors of D. So we stop. Now what are the values in the priority queue? These are B, C, and E. E has a distance of 7, 14 and 8. So which is the minimum? This 7 is the minimum. So we pop it from the queue and this distance is finalized. Now we look at its neighbors. Its neighbors are C. So its distance is 7 plus 6, 13. So we got a better value. So 13, and its previous is E. So this we have visited. Next is A, but that's not in the queue. So we don't need to update it. We will not get a better solution anyway for the nodes which are popped from the queue. You can see it here also, it's 7, and from here you will take another 7 to reach here. That will be 14, which will be more than 0. So we have looked at the neighbors of this. Now what are the nodes in priority queue? B and C. B has a level of 8, C has a level of 13. So B will be the next node. And its neighbors are C only, others are popped out. So it's 8 and we get a path of 1 here, edge of 1. So 8 plus 1, 9. So we can reach here in 9 units, 9 distance from the source, and we come here from B. So this time previous is updated to B. Now only one element, only one vertex is in the priority queue. So we will pop that, and now the queue becomes empty, so we stop. So what are the final levels? Let me write. A is at a distance of 0, B is at a distance of 8, C is at a distance of 9, D is at a distance of 5, and E is at a distance of 7. And we have also stored the previous. Previous for source will be null. So you can write maybe 5. So let's say I want to find the path from A to E. This was the path from A to C. Let's say we want to path from A to E. We already know the distance 7. So what we will do, we will start from this destination. We will see where did we come to E. What was the best path that led to E. So we came to E from D. This was the last update. So E is here, the destination, previous is D. Next we look at the previous of D. Previous of D is A. Next previous, we have reached the source, so we stop. So we print it in reverse order, that is A to D to E. So this is how Dijkstra algorithm works. You can calculate the distance of all the nodes from a given source, and you can also find the exact paths. There are other ways of implementing it also. Here I had used priority queue for implementing this. There is other way that you can, instead of inserting this into the priority queue, you keep a set. So you keep a shortest path tree set. Let's call it S. Initially it's empty. So you assign distance levels again. So d v equal to infinity for all vertices v belonging to graph G. Distance of source is 0, and initially this set is empty. So now we have assigned distance level to each vertex including source. So we do u will be extract min or min distance for all vertices. So the source will be picked. So u is source. Then we look at for all v adjacent to u, just like our earlier algorithm. It's that instead of putting everything in priority queue, we are building the shortest path tree set one by one, starting from empty set. So we will again check if d of v is more than d of u plus LUV, then d of v will be equal to d of u plus LUV, and you can also store the previous here, previous v equal to u. And again the levels are updated, distance level. Again you will extract the minimum distance from the remaining vertices. Again do the same thing, and ultimately until S contains all vertices of G. So here we are inserting nodes one by one in this. In the earlier approach, we had inserted everything in the priority queue and removing one by one till queue became empty. So this is another way of implementing it. So I hope you understood the concept of Dijkstra algorithm. It's very intuitive. It's one of the algorithms which is considered tough, but it's very intuitive. You start from a source node, you look at its neighbors. So whichever is minimum, obviously there will not be any way of reaching it with a distance less than this. Why cannot we find a better path from source to D whose length is less than 5? Because from A you can only go to these many nodes, in this case 2. So either you can go to B or you can go to D, and D is the shortest edge going from source. So any other edge coming to this will have to take another route, but that another route, even the first edge will be more than this minimum, since this is the minimum. So if you take any other path and come to it, the first edge itself is more than this, so the total will be obviously more than this. So that's why we finalize one node at a time. So this was final, then we made this as final and look at its neighbor and kept on updating. And here we are working with positive edges. So this will not work if edges are negative, because in that case, let's say this is 10, maybe there is a edge of like this coming here with minus 8, so total will be 2. Here it's 5. So it's for positive edges. For negative edges we have another algorithm called Bellman-Ford algorithm that takes more time than this algorithm. So the time complexity for this is v square log v, where v is the number of vertices, and in general edges in the graph are can be of the order of v square in worst case. So each node is connected to every other node. So we can have n multiplied by n minus 1 by 2. So edges are considered to be of the order of v square unless the graph is very sparse. And the time complexity for this Dijkstra is v square log v. If you have negative edges, then you cannot use Dijkstra. You have to use Bellman-Ford. And there the time complexity will be v cube. So you see log v square is common, log v versus v. So that takes more time than this algorithm.